In this lesson, we'll cover the derivative at a point of a function. So to start with a definition, the derivative of f at x is equal to a is the slope of the tangent line to the graph at the point a, f of a. When we started this class, we tried to find slopes of tangent lines, and we had to estimate them. Today, what we're going to do is introduce formulas that will find those slopes exactly, and these formulas will have limits in them. First, just a little bit of notation. If you see the symbol f prime of a, this is the derivative of f at x is equal to a. So this symbol means we're finding the slope of the tangent line at the value a. Now there's two separate formulas, and I'd like to use this graph to explain where they come from. On our graph, let's say you want to estimate the slope of the tangent line at x is equal to a, and I'll put that value a right here. So that's the goal. You want to find the slope of this tangent line. The way we did this was by choosing a point that was close to a. I'll put that over here and I'll call it x. And we found the corresponding y values at x and a, and we didn't find the slope of the tangent line, but we found the slope of the secant line going between the points at a and x. So the y value here is f of x, so I'll put this as f of x, and the y value that is here is f of a, so I'll call it f of a. And what we did is we said, oh, well, if I want the slope of that line, that slope is equal to f of x minus f of a all over x minus a. And this thing here is an estimate of the slope of the tangent line. How did we get a better estimate? We took this value of x and moved it closer and closer and closer until we got to a. What does that mean in terms of limits? That is the limit as x approaches a. And that's what this formula says here. It says if you want the slope of the tangent line at x is equal to a, you first choose a point different than a and find the slope of the secant line. The closer x gets to a, the better your estimate is. And in fact, if you take the limit as x approaches a, then you get the exact value. So this justifies one of our formulas, that this is f prime of a. Now there's an alternate formula here that we'll be using as well, and it looks similar, but there are a few differences. Another way you could express this formula is by saying, instead of calling this point x, you can call this distance here h. And that way x becomes a plus h, meaning h is some positive number, and if you add it to a, it'll take you to this spot here, which is also a plus h. If you call this a plus h, well, this is the same thing as f of a plus h. Using this notation, what you can do in the slope formula is say, all right, well, this is f of a plus h minus f of a all over a plus h minus a. So it's essentially this, except instead of x's, we're saying a plus h, where h is some small but positive value. If you simplify this, there's not much to do, but you have an a and a negative a, and this becomes f of a plus h minus f of a all over h. So this and this are equivalent. Here, we let x approach a, meaning the value x gets closer to this spot here. Down here, there are no x's, but you still want to use a limit. Saying x gets closer to a is the same thing as saying h gets smaller and closer to 0. And for this reason, this is also a formula for the derivative of f at x is equal to a. They'll be similar in their application, but sometimes this might be preferable to this definition here. But before moving on, the idea is we were talking about slopes of tangent lines. We're going to more formally call that a derivative. They have these formulas, and they're quite abstract looking, but they do come from the process that we used, where this part is the equation of slope. This part with the limit means put the 2 points really close together. and the closer you get, the more exact your answer is. Let's try this in example 1, where f of x is equal to x squared is this part of the graph here. And I'm going to use this definition to find the derivative at 1, the derivative at -1, and also the derivative at 0, the slopes of the tangent lines. Let's start with f prime of 1. F prime of 1, according to the definition, is, and I'll use the very first one I introduced, that's the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. I simply put 1 in place of a. Now this thing is the limit as x approaches 1 of, well, what's f of x? We have a formula for it. It's x squared. What's f of 1? Well, if you put 1 into this function, you get 1 back. And this is divided by x minus 1. If you want to find f prime of 1, which is the slope of the tangent line here, you have to solve this limit. And we've done stuff like this before. This one's not too hard to solve. I can factor the top and cancel the x minus 1. Let's try it. This is the limit as x approaches 1 of, the top is x minus 1 times x plus 1. It's a difference of squares, divided by x minus 1. You can cancel the factors of x minus 1. This leaves you with the limit as x approaches 1 of just x plus 1. And you can directly substitute 1 in place of x. And you get that f prime of 1 is equal to 2. So if you draw the tangent line here, the slope of this line is 2. And that's what all of this work tells us. This is not an estimate. This is the exact value of the slope of this tangent line. What about at -1? This graph is symmetric over the y-axis. I'm guessing the slope at -1 will be the negative of the slope here, meaning since this slope was positive 2, I'm thinking this slope will be -2. Let's try it. Okay, so f prime of -1 is the limit as x approaches -1 of f of x minus f of -1 all over x minus -1. So in the denominator, the two negatives make it positive. This is the limit as x goes to -1 of f of x is x squared, and f of -1 is positive 1 again, so it remains x minus 1, and this is divided by x plus 1. This is equal to the limit as x goes to -1 of, that's the same difference of squares. It's x minus 1 times x plus 1. And this time, x minus 1 won't cancel, but x plus 1 will. So this is the limit as x approaches -1 of x minus 1. And if you simply directly substitute -1 in place of x, you get -2, which was the answer I was anticipating. This here, this slope is -2. The last one I have here is, what is the derivative at 0? Can you guess? If you were to draw a tangent line at this spot, it looks like you'd have a horizontal line, and the slope of that line should be 0. I'm anticipating that the answer is in fact 0, but let's just check just to make sure. Okay, so this is going to be f prime of 0. That's the limit as x goes to 0 of f of x minus f of 0 all over x minus 0. That's the limit as x goes to 0 of, well, that's going to simplify really nice. F of x is x squared. F of 0 is 0. I won't write it. And then we have x in the denominator. You can simplify that too. X squared over x is simply x. And by direct substitution, you do in fact get 0. So the slope here is 0. This all came from this definition here. We could have used the other definition and ended up with the same answers. You might want to try that. But for this problem, I think that's good enough. This notation means we're finding slopes of tangent lines at the points we started with 1, -1, and then we had 0. In example 2, let's look at a more complicated function. F of x is equal to x squared plus 2x minus 1. I want to do two things. I want to find f prime of 3. That's the slope of the tangent line at 3 on this function. But then I also would like to find the equation of this tangent line at 3. And for this one, I'm going to use our other definition. That is, f prime of 3 is equal to the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. If we simplify this, this is the limit as h goes to 0 of, what is f of 3 plus h? This means wherever you see an x, you will put 3 plus h in place of that x. So this first part is 3 plus h squared plus 2 times 3 plus h, then minus 1. So that is, this thing here is simply taking this equation and replacing all the x's with a 3 plus h. I now want to subtract whatever f of 3 is equal to. And that means you put 3 into this function. So it's 9 plus 6, that's 15, minus 1 is 14. So I'll note off to the side here that f of 3 is actually equal to 14. Okay, I want to simplify this thing. The goal for this limit is, in the denominator there is an h. Can we somehow simplify this thing so I can cancel this h, allowing me to put 0 into the remaining expression? Let's see. In order to simplify this, there isn't a whole lot to do, but maybe I'll square out 3 plus h. So I'll square this thing. You square the first and the last terms, but you get 2 middle terms as well. So that is 3 plus h squared is 9. Now your middle terms are going to be a 3h and a second 3h, which is 6h, and then if you square h, you get h squared. Here, if you distribute the 2 into the parentheses, you get plus 6 plus 2h, and minus 1 and minus 14 is minus 15. And this is still all divided by h. Okay, does anything simplify or cancel or combine? Oh, I see. This is the limit as h goes to 0 of, well, 9 and 6 is 15, and minus 15 is 0. So in this step, you add those two and subtract this, and there's nothing left over. There's also a 6h and a 2h, which sums to 8h. The only thing left is the h squared. This is what the process looks like using the other formula. Square stuff out, combine like terms and cancel, and here we have this expression. I can factor an h out from both of these terms and cancel it with the h in the denominator. This is the limit as h goes to 0 of h times 8 plus h all over h. This cancels with that. This is the limit as h goes to 0 of 8 plus h, and directly substituting 0 in for h gives us 8. That's f prime of 3. And what is that? That's the slope of the tangent line at a is equal to 3. In this question, we're also asked for the equation of the tangent line. You can either use y is equal to mx plus b, or y minus y1 is equal to m times x minus x1, and both will work. I prefer to use this one just because I have an x1 and a y1, and I also know the value of m, and I can directly plug those into this formula. Since I want the equation of this line, I first have to know, well, what value are we using for x and y? That's the value of the function at 3, which is 14. And the reason is we're drawing the tangent line here. So, again, I'll just note that, well, this is my x1 and this is my y1. And here, this thing is my value for m. In the formula, we get y minus 14 is equal to 8 times x minus 3. Easy enough to simplify. you can distribute the 8, and then you can add the 14 to the other side. And we have this equation here. This is the final answer to this problem. In example 3, we're given that f is equal to 2 plus x minus x cubed. And we want to find f prime of, well, a, and here it's just a instead of just a specific number. When you see this, this means we're actually going to find a general formula for the derivative. There's a benefit to this. This computation of finding f prime of a is a lengthy one. And if you want to know, let's say, f prime of 1, f prime of 7, f prime of -3, you wouldn't want to have to do the limit definition 3 times in a row. It'd be better if you get a general formula for a and then put 1, 7, and -3 into it. So that's what we're going to do here. So let's try it out. To find f prime of a, I'm going to use the limit as h goes to 0 of, and I'm going to use the second form of the definition. First, I want f of a plus h. I'll subtract off f of a and divide by h. Well, what is f of a plus h? That means in this equation, wherever you see an x, you'll put a plus h. That is 2 plus a plus h minus a plus h cubed. Note here that I didn't need parentheses here because there's a 1 in front of the x. Now, second, I want to subtract f of a, which means you're subtracting this function with an a in place of both h's. Something to be careful about here. When you're subtracting a function with multiple parts, put parentheses around it like this. And the reason is, when you subtract the entire function, this negative will be distributed to all 3 terms. And here we're dividing by h. Okay, the trick for this problem is going to be cube this out, multiply by -1, distribute this negative, combine like terms, ultimately canceling this h from the denominator. I'm going to do a little work off to the side. That is, what is a plus h cubed? It's a cubed plus 3a squared h plus 3ah squared plus h cubed. There's a nice pattern going from this to this. If you cube something, a lot like squaring it, it'll start with a squared. And as you move down the line, the exponents on a drop by 1, from 3 to 2 to 1 to 0, which isn't even written. And in reverse, the h's start at 0 and increase until you get to h cubed. So you have h to the 0, h to the first, second, and third. The last part is, what are the coefficients in front of these items? It's 1, 3, 3, and 1. You can quickly find those coefficients by looking at something called Pascal's triangle. So sometimes these computations can be quite lengthy, and it's nice to maybe note what a plus h cubed is outside over here so you can quickly plug it back in here. In my next line, when I simplify, I'm looking at the limit as h goes to 0 of, and there's going to be a lot of stuff. But what I'm going to do is put down 2 plus a plus h, and I'm going to take this negative and distribute it to all of these terms. They'll all become negative. I'll also multiply this negative into the parentheses. We have 2 plus a plus h minus a cubed minus 3a squared h minus 3ah squared minus h cubed. Furthermore, we have minus 2 minus a, but then plus a cubed. And this is all divided by h. A lot of stuff should cancel. Oh, we have a 2 and a -2, so I can cancel those. This cancels with that. I have a positive and negative a. Those cancel, as well as a negative and a positive a cubed. I don't think anything else combines, so I'll write, well, this is the limit as h goes to 0 of. Okay, we have h minus 3a squared h minus 3ah squared minus h cubed. And I think that's it. And this is all divided by h. I'm noticing that there is at least one h in every single term, meaning I can factor them out and cancel it with this h. That's the limit as h goes to 0 of h times 1 minus 3a squared minus 3ah minus h squared. I can cancel this h. The last thing to do is figure out the limit as h goes to 0 of 1 minus 3a squared minus 3ah minus h squared. We can simply put 0 into all of the h's. What is left is a 1 minus 3a squared. This is f prime of a. It's a formula that depends on a. Now that you have a general formula, you can simply, to find these three things, put 1, 7, and negative 3 in place of a, and you'll quickly get your answer. So to recap, this formula seemed to work pretty nice here because we were squaring or cubing things out. I plugged all this information in, cancel as much stuff as possible, factored out an h to cancel it. I ended up here. I saw this term and this term had h's in it. They both went to 0, so I didn't include them in my answer. And let's look at one more, where here we have f of x is equal to 1 over x. Can we find a general formula for the derivative f prime of a? For this one, I think you could use either definition. I'm going to use the first definition. That is, f prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. This is the limit as x approaches a of, well, f of x is 1 over x. I'll leave some space. We'll subtract off the function at a, which is 1 over a, and this is divided by x minus a. If you have fractions within fractions, using a least common denominator is a nice way to try to cancel them. The common denominator is actually a times x. I'm going to multiply that to the numerator and the denominator. Here's what we get. This is the limit as x approaches a of. Okay, so it's going to be ax over x minus ax over a. And in the denominator, I'll just put x minus a times ax. So I multiplied the top by ax, so it went to this term and this term. And then I multiplied it to the denominator too. I chose not to distribute it in. What cancels? This x and that x, this a and that a. And now we have the limit as x approaches a of. So in the top, we just have a minus x. I think in the denominator, I'll put a x first and then x minus a. So at least the fractions within fractions thing is gone. Now, I'd like to cancel this x minus a so I could put a into all of the x's. I'd really like to cancel this with this, but they're not exactly the same. But there's a trick we can do here. We can factor out a -1 from this, and I'll put that over here. This is the limit as x approaches a of negative, and it's got to be x minus a. And the reason is, if you take the negative and multiply it back in, you get a negative x, which is what we want, and also a positive a, which is, again, what we want. We are now allowed to say, well, this cancels with that. This is the limit as x approaches a of -1 over ax. Can we directly put a in place of x to get our answer now? And the answer is yeah. We get -1 over a times a, which is -1 over a squared. This is the formula at x is equal to a. One final thing to note is here, 0 is not a value you can put in place of f, so there is no derivative at 0. And notice in your formula, you can't use a is equal to 0. So it actually matches up that where your function's not defined, in your derivative, it's a number that you couldn't use in the formula anyway. And that is it for this problem.